Let's now move to the Lasso. So far we have seen how to use regularization in the context of ridge regression, which is also known as Tikhonov regularization, as I mentioned, and sometimes, especially in the context of neural networks, is also known as weight decay. This is all the same thing effectively, and it's just looking at our previous regression problem. This is called the standard loss function for linear regression, and we just added this new term, which is the penalty term, so plus lambda times some penalty term here, and this penalty term is just effectively the total sum over all the regression coefficients squared. So sometimes people like to write this bit also as a kind of it's the L2 norm of the vector A. It's another way of writing this sum. It's the sum over all the components squared. This is called the L2 norm in mathematics, and that's why sometimes we call this regularizer also the L2 regularizer, because the penalty term is just the L2 norm of the weight vector. So that's what it is. Now, Lasso, in principle, the extension to Lasso is very straightforward. All we do is say, rather than using AI squared, we use the absolute value. We motivated earlier that we want something positive because AI can be both positive and negative, and we want it to be closer to zero. So we want to kind of constrain this sum, but it could be the sum of the squares or the sum of the absolute values. And Lasso is exactly the same, but where instead of the L2 regularizer, we now use the L1 regularizer, which effectively it's, rather than using squared, we use absolute value, and this sometimes also is called the L1 norm here. So this would be L2 norm, and this would be the L1 norm. Sometimes, sorry, people like to write the index at the bottom. Doesn't really matter. So L2 norm and L1 norm, those are the different norms, and those are the regularizers. So looks like a rather straightforward extension, and you might ask yourself, well, what can possibly what can possibly be so different about using a different form of norm here? But we will actually see that this will actually make some of the AIs to go exactly to zero, and this is actually quite something quite fascinating, because well, we wouldn't expected it naively that this little change makes such a big difference, but it actually does, and I want to explain to you in the following slide how it comes about. So let's just talk a little bit more about it on the board. I forgot to add the white page, so let me do it right now. So so let's just look again at the two optimization problems. So we want to minimize over all A. We have our least squares loss function, which is something like sum over I, yi minus f of xi squared. And now we had these two different penalty terms, which we could write in the kind of soft version. But for this discussion, it's actually easier to write it as a hard constraint. So, so we had the option like subject to, now that the sum over the AI squares is less or equal to C. I added the absolute value, but absolute value squared and absolute value is the same thing, so don't worry about that. And the sum over the AI absolute value is less or equal than C. So those are the two options, it's subject to this or subject to that, so one or the other. So this one here is ridge regression, and this one here is Lasso. So to see the difference, it's easiest to draw a picture. So let's just assume, for the sake of the picture, that we only have two dimensions, two predictors there, which coefficients are A1 and A2. So they are the coefficients A1 and A2. So if we just look at this optimization problem here. Let's just look at the loss function. Let's just ignore those constraints for a moment. Just looking at the loss function, I know that this function is quadratic, so it's quadratic in all the coefficients, because obviously the linear regression is linear in the predictors xi, but it's also linear in the coefficients ai. So this whole function is quadratic. It's a convex function, nice quadratic function of the ai's. So we know that this function is a quadratic, and we can just very easily kind of draw it. We know that a quadratic in 1D is just this parabola shape. Now in a quadratic in 2D is something which looks a bit like this. I will be trying to make a 3D picture, so something which looks like this. So this is a kind of parabola in 3D, but again, it's easier to kind of plot the projection exactly as you do with the mountains, rather than trying to draw a mountain in 3D. I'm just trying to draw the height lines of the mountain. So there will be some form of minimum here. So this might be the minimum of the loss function. And now I have some form of kind of height lines around it. And so on and so forth. So this would be, the minimum would be here, and the kind of optimal solution to this problem, if I run the minimization, it would try to find this point. This would be the optimal slope of the predictor x1, and this would be the optimal slope of the predictor x2. Each coefficient is called a1 and a2, and I call hat for the kind of solution to this minimization problem. So this would just be the problem of the unconstrained, if I had no constraints. So if those constraints weren't there, I would just get this solution here, which is the minimum. Now obviously we are interested in the constraint, and so how do those constraints look like? I have the condition here that ai squared and ai absolute value is less than some constant c, and I can actually look at those constraints here. So for example, let's just start with this constraint here. Such a constraint will just look like a circle, the condition like a1 squared plus a2 squared and so on equal to c squared or equal to r squared would be just the equation of a circle basically. So c would be equivalent to r squared. So what I have here is effectively the equation of a circle. So this region here I'm drawing would be the region where I have that the sum over ai squared, or I called it the L2 norm, is less or equal than c. So c would just be the radius squared of this circle here. Obviously, if I'm asked for the solution for the ridge regression here, now if I want to look at the solution in this optimization problem, including the first constraints, I will not anymore get this solution, which is the minimum to the unconstrained problem, but I will find the smallest value which is within this constraint. And here I can see what is the smallest value of our loss function, which is highlighted by this kind of mountain circles there, which is still within the shaded region, which is within the constraint. And this is exactly this point here. So this point will be the solution to the coefficients from the ridge regression. So I will get those 2 points here as a solution if I run the ridge regression. Okay, and now we can look a little bit what would look different if we had an L1 constraint. And what you can actually see is that for an L1 constraint, which would be this one here, I will, difficult to draw, So the L1 constraint will look a little bit like this diamond shape. It's just, this is what it looks like if the absolute value is less than some C. So the kind of region within the constraint will just be this green diamond here. So the green diamond will be this region where I have that the L1 norm is less or equal to some C. Now, what would be the best kind of minimum point on this loss function, which is closest to which is still within the constrained region? It would just be this point here, this is just intersecting with this height line here, the one which I've drawn here. This is this kind of height line. So this is the closest, the kind of smallest height line I have, closest to the minimum point, which is still within this region. And you see, it's just touching the region at this endpoint here, this endpoint. And because of this, we have the fact that one of the coefficients is 0. So now we can see that actually my coefficient A1 hat will just be 0 now, whereas A2 hat will just be this point here. So effectively, due to this to the nature of this constraint, the L2 constraint is this nice circular shape, or in higher dimensions some form of ball. And this ball will effectively always touch this height line somewhere in the interior, as you see in this case here. Because it just touches the height line in the interior, I will have shrunken the coefficients. You see here, A1 and A2 were considerably larger. Now I have shrunken them. Both are smaller. So A1 is now got smaller. A2 also got smaller. But none of them got to 0, because I'm more likely to touch the smallest height line somewhere in the interior region. Whereas for this other boundary, for the one of the L1 regularizer, I'm effectively more likely to touch the boundary at this endpoint here. And at this endpoint, at this kind of spikes of this shape, I will have always one of the coefficients being 0. For example, here A1 is 0 and A2 is non-zero. But this is just a two-dimensional picture, but the same idea also holds for the kind of higher dimensional analog. And this is the kind of graphical explanation why when we have the L1 regularization, I will actually have some of the coefficients exactly being shrunken to 0. And this is my hand-drawn explanation, but here you can see another picture from the textbooks. They called it beta and not A, but it's the same idea there. So if I have this is my quadratic unconstrained solution. The unconstrained solution would be here. But if I have a constraint problem, I have to find for a solution inside of this shaded region, which for the L2 norm would be somewhere here, but for the L1 norm is exactly at the corner, which makes one of the coefficients being exactly 0. And this is something very nice. At least for several applications, it is nice. If you're just interested in the cross-validation into the kind of lowest error, then whether you use the kind of right-hand side or the left-hand side doesn't really matter, because the coefficients are somewhat close and you will get a similar error as the output of the model. But it's very important if you look for some interpretation there, because the Lasso will effectively choose some of the coefficients to be exactly 0. This means that the predictor associated with beta 1 or A1 in our case is just not relevant to the problem, and this helps me to interpret. And in a sense, as I mentioned earlier, this is quite similar to the subset selection. Effectively now, this Lasso message selected predictor 2 and discarded predictor 1. So it does some selection of parameters. And now I've shown it for a kind of a fixed number of C, but obviously as I vary C, this shaded region can get bigger and smaller, and you can see that that actually corresponds to more and more predictors getting 0. I already know from the formulation of the problem, if I go back to this case here, I know that for example, if if lambda is equal to 0, or correspondingly the budget C is infinite, then I'm back to the original problem. Then all the coefficients will be non-zero. But I also know that if I choose lambda being infinite or C being 0, then I will have all coefficients going to 0. I can actually see that if I vary lambda kind of continuously, more and more of these coefficients will effectively go to 0 and disappear. And here's a nice picture which shows it. So this is effectively a picture, it's from the textbook, it's from the Elements of Statistical Learning textbook, and it's a kind of medical example. It talks about prostate cancer and is looking for some antigen of prostate cancer, and it looks how can I kind of predict this, the kind of quantity of this antigen using some predictor variables here. And I can see as I vary this parameter at the bottom, so this parameter is called shrinkage parameter, but that's effectively C. That's effectively a rescaled version of C here. It's kind of proportional to C, or inverse proportional to lambda. So here I have this value here, I have maximum value of maximum value of C, in which case I have no constraints really, or no relevant constraints. So C is large enough so that so for example, you can think of it, if C is large enough, if I increase C here, if my C would be as big as this, it will include the minimum, sorry, this square is a bit not very centric, so if I draw it like this, as I increase C, I will just be increasing this diamond there, and once this diamond includes my original minimum, then I will get the same solution as if I had no constraints. So and this point, this value of C for which it just touches it, this value is just chosen to be 1 in this example. So this is the case, this is the value of C where I effectively have no constraints going on here. So now I have all coefficients being different to 0. So those are the different variables, and for example, this LCA vol is, I think, the log cancer volume or something like this, and it has a rather high coefficient, so it's positively correlated, and it has a high coefficient. Other ones like Gleason score as a medical parameter has a very small coefficient. I can see as I now reduce the cost function or correspondingly increase lambda, some of the variables will drop to 0. You can see the first one who drops to 0 is this Gleason score. It will be disappearing. So if I choose this value of C, for example, or correspondingly the value of lambda, which is just inversely related, I will have all variables in my model apart from the Gleason factor now, or Gleason score. Now if I go on, I will drop other variables. So here you have H, for example. So H will disappear, and LCP, other variables will disappear. If I choose now this one here as my value of C, I will have all variables but those 3 at the bottom there. And kind of, if I choose a C here, I will only have one variable left. In this case, only the cancer or the logarithmic cancer volume is left. So now I have just one variable left there. And if I were looking for a model, the best model which describes this with one variable, this will be the variable I would get. And if I choose C even further, if I choose the cost function all the way down to 0, then my last coefficient will also disappear. Now I'm just left with an intercept, basically. But what I wanted to show you is nicely how these variables kind of shrink to 0. If I would have a ridge regression, they will kind of become smaller, but they will never go exactly to 0. So all these lines would be kind of approaching the x-axis, but they will never go exactly to 0. So I can't really ever say which ones are kind of selected and which one are not selected. Here I have a natural kind of subset selection. All I have to do is kind of propagate through the picture from right to left, and I can see how different variables will basically be dropping out one after the other. So yeah, as I said kind of earlier already, so shrinkage is very important because we see we can kind of control flexibility by just controlling a single variable. So if you do cross-validation, if you look at this bias variance trade-off, actually varying lambda will be the easiest way of actually dealing with kind of varying the complexity of the model. And really any model in machine learning has this form, as I already mentioned earlier, where I have some kind of optimization objective, something I want to minimize, which is just some loss shrinkage term times some regularizer. And we will see how different models often just differ by the choice of loss function or maybe the choice of regularizer. We saw like rich regression and Lasso are basically the same thing. It's just L2 versus L1 or a regularizer, whereas other models could be similar, and I could just have a different loss function, for example. You can do the same thing also with logistic regression. I could choose logistic regression, plug in the loss function of logistic regression. I can just add a regularizer to logistic regression. No reason why I could not do that. And so, as I just said, you can do the same thing for classification as well. And there are also other regularizers. So, for example, I could just also look at a combination here. This is a kind of a blending which uses both a L2 as well as an L1 norm here. And this is sometimes also called the elastic net, which you can see here. So one of the kind of original papers which introduces the Lasso also introduces the elastic net, which is a kind of more general way of dealing with it. You could see if alpha is equal to 1, I get rich regression. If alpha is equal to 0, I will get Lasso, and I can basically interpret between them. Most importantly, so the rich regression is obviously still rich regression is linear, which means that the combination, so this loss function, most importantly, both loss function here are still convex. So it kind of so this is a convex function, we already talked about it, but this is a convex function as well. Nothing changes here, but you couldn't use any other kind of smaller norm. One is the smallest you could change if you, and this is also, you can see it from this picture I was showing earlier, kind of like this. Now Lasso would be the straight line, but I couldn't have anything which is kind of inward bounding, because this wouldn't give me a convex optimization problem. Then I couldn't solve it anymore, not even numerically. So this is basically all I wanted to say about the Lasso. Now we will talk a little bit about high dimensional statistics, where Lasso also plays an important role.